cover the basics of developing XR applications, which require animated 3D models that appear realistic, interact with the virtual world, and generate feedback that the user can sense or feel. Let's start with how the 3D models are represented. For performance purposes, the virtual objects that we use in XR applications are hollow shells made of polygons. This means that the 3D objects have no content, meaning there will be no pulp inside a virtual apple, just an exterior shell. The shell is approximated with polygons. The more polygons, the closer the approximation to reality. When the objects represented are faceted, like the yellow cube in the video, the polygonal modeling shows no differences from reality. The polygonal representation of a virtual object starts with specifying the corner vertices. Referring to the video, the cube has 8 corners, hence, there will be 8 vertices, each specified with its x, y, and z coordinates relative to the world reference frame, shown in the center with axis x, y, and z colored in red, green, and blue respectively. The black vectors going from the origin to vertices 1 and 3 are examples of position vectors of the vertices and have the coordinates shown in the vertices list. The polygons are then defined as lists of vertices shown in the list. Depending on how the model is created, each of the 6 polygons can be split into triangles along one of the diagonals. In such a case, the polygon list would be longer and contain 3 vertex polygons, meaning triangles. Using this technique, we can model the shape of any object, as shown with the red sphere at the bottom. Even though a sphere has no flat surfaces, it can be approximated successfully with a larger number of smaller polygons. The larger the number, the better the approximation. Changing the position of the cube would require changing the coordinates of each vector. From a modeling point of view, this is cumbersome because it breaks the intuitive way of thinking, move the object, and instead we must think of moving each vertex. The cause of this is that the object vertices are positioned with respect to the world reference frame. We can make the object position change more comfortable by defining a reference frame x, y, z local to the object, and representing the vertex positions relative to it, as shown in the vertices list. This is exemplified visually by the purple vector pointing to vertex 3. The local reference frame will have a position relative to the world reference frame, shown as the black vector pointing to vertex 1. Notice how the local reference frame, because it overlaps vertex 1, has the same position as it had in world coordinates, and vertex 1 has coordinates 0, 0, 0 locally. Vertex 7 being diagonally across from vertex 1 has coordinates 1, 1, 1. The position vector of each vertex, as exemplified by the long black vector pointing to vertex 3, will be computed by adding the local reference frame position in the world coordinates with the vertex position in the local coordinates. You can easily see how the short black vector being the local reference frame position and the purple vector being the local position of vertex 3 are placed end to end. Thus, their sum is the long black vector, which is the world coordinates position of vertex 3. Take a moment and observe these vectors and their relationships. The vertices and polygons discussed up to this point specify only the shape of the object. The appearance of the object is determined by colors and its interaction with the light, which is influenced by the vector normal to the surface. The color are usually attached to the vertices, while the normal are attached to the polygons. The cube is yellow in color and it is 75% opaque, thus the 1, 1, 0 color specified next to the vertex coordinates and the 0.75 alpha value following the colors. The normal are specified for each polygon after its list of vertices. Since the yellow cube is aligned with the reference frame, it is easy to determine the normal to its faces. The normals must always point outward from the object, hence the normal of polygon 2 is the same as axis x. The effect of lighting on an object cannot be calculated without the polygon normals. If the model does not contain normals, they are calculated as the vectorial product of neighboring polygon sides. For instance, for polygon 2, the normal would be calculated automatically as the vectorial product of the vectors defined by segments 2, 6, and 2, 3. This works quite well as long as the resulting normals are pointing outward. To ensure that, the vertex polygons are specified in counterclockwise order. Now that we have seen how to specify the position of an object in the virtual world, let's see how we can specify its orientation. At the most basic level, rotating an object results in modifying its vertex coordinates. Just as we have done with the position, instead of moving each vertex individually, we will make use again of the local reference frame. If we rotate the local reference frame and then compute the new vertex positions just like we've seen, the result will be a rotated object just as expected. The problem of rotating an object is reduced to just rotating a reference frame. You can see here 5 ways to represent a rotation, the first 3 of them being shown by the rotating frames. All 3 frames start from the same initial orientation and reach the same final orientation of being rotated 45 degrees around each axis. You may notice some discrepancies between the frames, especially about the orientation of the green y-axis, but those are slight deformations caused by looking at the frames from very up close. The first rotation method is to rotate the frame around the original x, y, and z axis, also called fixed axis. We first rotate by 45 degrees around the y-axis. Then we rotate by another 45 degrees around the fixed x-axis, shown smaller and in bright red. Finally, we rotate again around the fixed z-axis. The same resulting orientation can be obtained by rotating around moving axes in reverse order, as shown with the second rotating frame. We first rotate by 45 degrees around the z-axis, then again around the new x-axis, and then again around the new y-axis. The resulting orientation is the same as that of the fixed axis rotations. The moving axis rotation angles are also called Euler angles. A third possibility is to determine an axis and the angle to rotate around it such that it takes the frame from the initial to the final orientation. This is called the axis angle rotation and can be seen in the third frame rotation. While these are intuitively easy to grasp, we need a mathematical way of expressing them. This is where the rotation matrix comes in. Before being rotated, the frame had the same orientation as the reference frame, meaning vector x was 1, 0, 0, vector y was 0, 1, 0, and vector z was 0, 0, 1. After being rotated, the 3 vector coordinates in the original reference frame have changed. If we name their coordinates I, j, and k and place them on columns in a 3 by 3 matrix, we get the rotation matrix. The beauty of the rotation matrix is that it can combine multiple rotations through simple matrix multiplication. Finally, the 5th rotation representation is the quaternion. It has 4 components, just like an axis angle, but these 4 components are not angles, nor vectors. They for a 4-dimensional vector, which offers high computational performance. All these 5 rotation representations are equivalent and can be converted from one to another. The position and orientation of an object, which is implicitly the position and orientation of its local reference frame, can be combined represented with a 4 by 4 matrix as shown in the equation. A transform matrix is formed adding the position vector as a column to the right of the rotation matrix and padding it with a 4th row containing zeros under the rotation and a 1 under the position. Transform matrices can combine both changes in position and orientation by simple matrix multiplication. This allows for a hierarchical positioning of virtual objects. For instance, consider the changes in position of each keyboard button on a laptop sitting in a bag carried by a person while riding a bus. Using hierarchical positioning, this becomes quite natural. All we need to do is to define parent-child relationships between objects and represent each object's position and orientation with respect to the parent object. The yellow cube in the animation is a child of world origin. Its position and orientation are defined by the transform matrix A. The blue cube is a child of the yellow cube, and its position and orientation are represented relative to the yellow cube using transform matrix B. This hierarchical structure of objects in parent-child relationships is called a scene graph, and it is the central data structure of an XR application. If we expand the notion of object to include sounds, lights, behaviors, and so on, you can see how modeling a moving car at night is just a matter of attaching the lights and sound to the proper locations on a 3D car model, and a spinning behavior to the wheels. The next step in our exploration of XR application development fundamentals is focused on the appearance of virtual objects, of which the most basic is the color. While we always talk about an object's color, the color that we perceive is heavily influenced by lighting. The same glossy white sheet of paper will have a different color in overcast daylight, under moonlight, or when a flashlight shines on it. The color of an object is not perceived uniformly, as the light reflections cause changes in nuance. Simulating lighting is essential for rendering realistic virtual objects. Realistic lighting is very computationally expensive due to the complex nature of light reflections. For movies, such complexities are acceptable as each movie frame is rendered and powerful servers without the need to do it at an interactive rate. The inherent interactivity of XR applications forces us to settle for simpler and less performant lighting approximations, but the results are still good. The most common light reflection model is the FOAM model you see on top. The light is split into three components: ambient, diffuse, and specular. When added together, these components yield a realistically looking 3D object. The ambient component is a dull low-intensity light that causes no shadows and gives no sense of depth. It is the way we see objects in very low light. We see their shape and vaguely guess at the color, but we cannot distinguish distances or object depth. The diffuse component is the light that falls on an object when shining a light on it. The side of the object facing the light will be bright and will progressively darken as it is sloping away from the light and eventually is just dark. The diffuse light gives a sense of depth to the objects, but it can only render matte surfaces. The specular component is the light that reflects from the object into the eye of the viewer. The specular component appears as small bright spots, which are the smaller the shinier the object is. Adding together these three components, we obtain a shiny-looking object that, thanks to the ambient component, is not completely dark in the places where the diffuse light doesn't reach. Using lighting and various colors for the polygons making up an object, we can create realistic models, but we can do even better if instead of coloring them polygon by polygon, we apply an image to the entire object. Such an image is called texture, and it is wrapped around the object by painstakingly specifying each polygon's corresponding area in the texture. Combining lighting with textures leads to amazingly realistic 3D models. Creating realistic objects can sometimes result in a very large polygon count per object. Large polygon counts are directly proportional to the interactive rate of the application. The more polygons, the lower the interactivity. An ingenious method of achieving high realism while keeping a low polygon count is the normal maps. Consider the rough spherical rock on the bottom right. It looks very real, but it also has a high polygon count that model all the little deformations on its surface. However, for the purposes of an XR simulation, those deformations do not justify the high rendering cost. The effect of surface deformations on an object's appearance is caused by the reflections and shadows they create. However, both those lights and those shadows contribute to the lighting algorithm with just color and normal. This means that instead of having so many polygons, we could have significantly less, but instead play with the normals to achieve the same effects. This is the idea of normal maps. They are simply textures whose colors are used as normal vectors. This is possible because both normals and colors are specified with three components. So, instead of having many polygons, we can apply to the object a texture like the one on the top left, and when calculating lighting, instead of taking color from the texture, we take a normal. That normal will cause reflections and shadows on a flat surface and trick the eye into seeing deformations. The one way in which the illusion fails is when you look at the edges of the left sphere. Since it only plays with light and has no deformations, its profile is perfectly round. Another technique for keeping a low polygon count is using LOD objects. LOD is an acronym for level of detail. LD objects are in fact a collection of multiple versions of the same object with various resolutions, from highest polygon count to barely a single polygon with a texture on it. The principle of LOD relies on recognizing that we cannot perceive the same amount of detail of faraway objects as in close objects. Hence, faraway objects should be rendered with less polygons, since their realism cannot be perceived anyway. This collection sphere starts with a high-resolution model where polygons are barely visible and appears to have a perfectly smooth surface. It progressively reduces the polygon count down to a version made of 15 polygons that does not resemble a sphere unless seen from very far away. The LD object associates each of these models with a distance from the viewer, switching between them as the viewer gets closer or farther. The lowest polygon count model is usually a single polygon with a texture of the original object on it. The polygon is rotated to always face the camera, and as it is away from the viewer, offers sufficient realism. Such viewer-facing polygons are called billboards and are used when having to render many objects that are far away. Examples where billboards can be used successfully are forests, with each tree being a billboard, and rain, with each raindrop being a billboard. Phenomena like fire, smoke, jets, or explosions cannot be modeled as polygonal objects because although they are finite in size, they do not really have a surface. Such phenomena are rather amorphous and change rapidly in shape, size, color, and transparency. Particle systems are a mechanism that employs large numbers of billboard polygons to simulate the phenomena above. Each billboard is a transparent polygon carrying a texture that resembles best a small part of the phenomena. For rain, it would be a drop of water. For smoke, a fuzzy gray circle that is transparent at the edges and almost opaque in the middle. These billboards are called particles and are created in large numbers, each having a lifetime and rules of how it evolves. For smoke, the particle moves upward and randomly sideways over its lifetime while growing, slowing down, and becoming more transparent. At the end of its lifetime, the particle is removed from the scene, thus the polygon count in the scene is kept mostly constant. You can see on the left a simplistic smoke simulation using a particle system. On the right, you can see a flight among the stars simulation that also uses a particle system. The particle emission, lifetime evolution, and disappearance is more obvious here. The next topic in our exploration of XR development is the foundation of any interaction. When we interact with the real world, we touch, grab, lift, drop, or throw things. All these actions start with touching. In a virtual environment, this equates to determining whether two objects touch each other. In other words, detecting the collision between objects. Perfect collision detection is complex and very computationally expensive because verifying whether any of an object's polygons intersects any of the other object's polygons. Furthermore, in some cases, we need to determine whether an object is completely inside another object, which means they intersect, even though none of their polygons touch. Depending on the polygon count and the number of objects that need to be checked against each other, this computation will soon bring any application to a halt. The solution is to approximate collisions using bounding volumes. Instead of checking the object's polygons against each other, we wrap each object in a simple shape such as a box or a sphere, and we verify collisions between these bounding volumes. Due to low polygon count and convex shape of the bounding volumes, collision detection is cheap and fast. The downside of this approach is the accuracy of detection. All these fir trees wrapped in bounding volumes will be considered intersecting, although only their bounding volume do. However, in most cases, the collision detection does not need to be more accurate than this. When necessary, accuracy can be improved by wrapping the model in several smaller bounding volumes that better approximate its shape. This will increase the computations, but it can also be activated only when the large bounding volumes detect a collision. When the bounding volumes are boxes, we can differentiate between axis-aligned bounding boxes ABB and object-aligned bounding boxes OBB. The ABBs are much faster in detecting collisions, but do not rotate along with the object, which can lead to poor approximations of the object shape. The OBBs rotate with the object and thus approximate the object shape better, but require more computations. Certain collision detection approaches fail when objects are moving very fast. To understand the problem, we need to understand that XR applications work frame by frame. This means that the application continuously draws the virtual scene on screen, each image being a frame. Every iteration, the application moves the virtual object according to the implemented rules and to the user interactions, and then draws the scene. While the scene is being drawn, the virtual objects are not moved or updated. This is only done in between frame rendering. While the duration of a frame rendering should be very short, it will still take a few milliseconds, during which virtual objects should move. When rendering is over and the application updates the scene, the objects are moved according to the time passed since the last update. Hence, if we have an object moving fast, it will cover a large distance between two such verifications. Consider the snooker player hitting the white ball towards the pink ball. Since the ball moves fast, it is possible that it will cover during a frame a distance larger than the ball diameter. The dashed circles show a hypothetical sequence of ball position updates. The collision verification against the pink ball will fail because at none of the verification moments the two balls intersect. This collision detection approach is discrete and it fails for fast-moving objects. In such cases, continuous collision detection algorithms should be used to verify the intersection between the path of the fast-moving object and the rest of the objects. Continuous collision detection will give accurate results, but it will also be computationally expensive. Finally, we reach the last of our exploration subjects, and that is physics. To achieve realism and immersion, the objects in the virtual environment should ideally move according to the laws of physics. While that can be implemented manually, the amount of collision detections and physics laws to be applied would make application development quite complex. Physics libraries solve this problem by supporting virtual objects to be decorated with physics qualities such as mass, velocity, acceleration, friction, bounciness, etc. All these attributes are then processed by a high-performance algorithm that calculates the object's positions based on the laws of physics. The physics involved are usually exclusively rigid body physics due to their lower computational needs. All the spheres falling are 3D visual objects whose movement is controlled automatically based on gravity and physical boundaries. The physics libraries have made their way into most mainstream XR frameworks and are helping development massively. Besides moving rigid bodies, physics libraries also support assembling objects using joints very similar to real-life methods. Two objects can be joined with a fixed joint, which is like gluing them together, possibly at a certain distance from one another. Linear joints connect two objects, letting them slide along each other like the piston and the cylinder of a bicycle pump. Hinge joints connect to objects, letting them swing around one another, like a door hinge. Universal joints are made of two perpendicular hinges and allow rotations around two axes. They are very similar in functioning to how telescopes are aimed at stars. Spherical joints are similar to the hip joint, allowing rotations around three axes. Their movement is similar to the universal joints, but in addition, they can also rotate around the shaft axis. The goal of this chapter was to introduce you to basic methods of implementing XR applications. It all starts with geometry and linear algebra, which makes it possible to position objects in 3D space. Transform matrices and hierarchical object positioning make scenes easier to manage, as multi-part objects can be manipulated as single entities through their top parents. There are complex modeling problems to be addressed, such as lighting and surface deformations. Proper solutions to such problems reduce the interactive rate of the application, but good enough, simplified, and fast solutions are available. The core of any interaction is collision detection and is consequently central to user-XR interactions. Realistic interactions require physical equations to be implemented, but physics libraries make this quite approachable for rigid body interactions.